Right, okay. Good evening, everyone. So we'll start the past paper discussion. Unit 3, we have some pending MCQs in oscillation wave section. And today we'll start past paper discussion regarding optic sections also. Before that, put some replies in the YouTube chat, whether you all can hear me speaking and audible and video is okay. Put a small reply. Give me a small confirmation via the YouTube chat. Give me a small confirmation via the YouTube chat. Give me a small reply. If all good, give me a small reply. This is not 2027 batch class. It is 2026 past paper class. Right? I shared the links in all the groups, but this class is 2026 past paper class. Because since we haven't just started oscillation waves in 2027 batch, you won't be able to understand anything in today's class. This is for the 2026 past paper class. Okay. All right. Okay. All good. Ne? Right. Okay. Now time is almost 6:45, 7:45, 8:45, 9:15. So we are taking our first break around 9:15 or 9:30. Then plan to do the class till maybe 11 till 11, sometimes 11:15 maximum. Maybe the plan is to do the class till 11. That's the story. Okay. We'll start the idea. Now I want someone to put some WhatsApp message. Okay. Now what are the pending questions available in past paper book 1? Oscillation waves unit 3. In my past paper book 1, what are the pending questions available? Right. Put a small WhatsApp message. I could not discuss the first section. Therefore, I will start discussing first section, first MCQs. As I can remember, I discussed all the simple harmonic motion, all the past paper MCQs. That section, all the MCQs are discussed. And then wave properties past paper questions I haven't discussed yet. Today I am discussing that story. I will discuss in a while wave properties MCQs. That is okay. And we completed transverse waves. If there are any MCQ pending in transverse waves, please someone put a reply with the WhatsApp. Transverse waves, I assume I completely discussed. Simple harmonic motion, I completely discussed. And then velocity of sound also, as I can remember, completely discussed. I discussed entirely velocity of sound. Longitudinal wave, that is also discussed. But I'm not sure whether we have some pending MCQs in longitudinal waves. Please someone put a WhatsApp message. If there are any MCQ pending, someone put the chapter and the question number. Okay. Other than that, the remaining stories, sound intensity, the questions discussed completely. And then electromagnetic waves also, other than laser ray, remaining questions are discussed. Okay. Someone put WhatsApp message. I will start discussing first story. Then we are going to the optics oscillation waves. And February tunes will be posted maybe next Monday, most probably. Worst scenario, sometimes it will be posted by next Friday. Worst scenario. Okay. So therefore, you will get the past paper book 2 under oscillation and waves. Parallelly, you will get the remaining target papers 21, 22, 23, 24, 25, 26. That's the plan. Okay. We'll start the story somehow. Time is almost 6:50. we'll start discussing questions. We'll start discussing questions. All right. Okay. Right. Okay. Right. Okay, now we'll start the story. We'll start the story. Now, wave properties, question number 1. A composite string which consists of two parts AB and BC with different mass per unit length is stretched to a given tension. Composite string which consists of two parts AB, BC, different mass per unit length. That means both the strings have different linear densities. Is stretched to a given tension. That means both the strings A and B have both strings A, B and BC have same tension, but both of them have different linear density, but both of them have same tension. The mass per unit length of AB is much smaller than that of BC. Okay. 1992 available wave property stories. Available wave properties ni wave properties wave properties wave properties wave properties. Available question. Right, MCQ number 1. Under wave properties. Okay. Now they have given two strings which have different linear densities A, B, B, C. And clearly mentioned AB string has the lower linear density, BC has the larger linear density. Right? This point is point A, point B, and point C. Okay. Then both the strings have same tension, but both of them have different linear density. Okay. Right. Then a pulse is set up in the string and it moves to the right along AB as shown in the figure. Now there is a wave pulse. It is propagating through the string AB to the right side direction. The wave pulse. The wave pulse. So what they're asking? After the pulse has reached the junction point capital B, the resulting pulse in the strings look like. Because we know that now in the beginning, this wave pulse propagating in the lighter string, right? Since they have mentioned this string has the lower linear density than string BC. Remember, for this string, this point capital B going to be a rigid boundary. Rigid boundary. For this wave pulse propagating in the lighter string, point capital B going to be a rigid boundary. Then we learned, if it is a rigid boundary, what will happen? What will happen? Wave pulse will completely inverted. Rigid boundary. Rigid boundary. During the reflection of this wave pulse at point capital B at rigid boundary, this wave pulse will be completely inverted. If not, the phase difference is 180 degree. That's what we learned. In a theory, we learned. We learned a theory, right? And also, if you can remember, a small wave pulse After incident at point capital B, a small part of the wave will be reflected backwards, but the phase difference is 180. A small wave pulse is propagating through the BC string. Okay. So we talked about this rigid reflection stories clearly we learned in our theory classes. So just after the reflection and the rigid boundary, if I draw the wave pulse propagating in string AB and string BC, it would be like this. It would be like this. Right. The wave pulse propagating in string AB going to be inverted. It's going to be inverted. If I do the shape, would be like this. But actually, when you compare with the amplitude of reflected wave pulse in AB string and this incident wave pulse in AB string, remember, this pulse has a relatively smaller amplitude than this pulse. That story also I taught you, if you can remember. We learned. And also, what will happen is, a small wave pulse is moving along the BC string to the right side direction. It has a very small amplitude. It has a very small amplitude. Is the story. This idea we learned already. Theory classes, we learn this idea. Right? Is the idea. So there are a lot to learn from this story. The first story is what? First story, some additional theory stories. Remember, for the wave pulse propagating in the lighter string, point capital B going to be rigid boundary. The rigid reflection occurs at point capital B. Therefore, this wave pulse propagating in the lighter string will be reflected with a phase difference of 180 degree. If not, we call it as inverted. That story. And when you compare the amplitudes, this amplitude is amplitude of the incident pulse, let's say capital A. Amplitude of this reflected pulse is capital A1. Amplitude of the pulse propagating in B string is capital A2. We learned, if you can remember, capital A is greater than A1 and A2. That story we know. This story we know, capital A is greater than A1 and A2. This side also we know. Therefore, the right answer for this question, the right answer going to be third one, right? Third one is the right answer. This question, third one going to right answer. Third one. Right, next story. Then 1995 A-level question. Right? Next idea. 1995 A-level question. These are basic questions. Everyone can understand these ideas. And if you have any doubts, you can ask for the YouTube chat. Question number 2. Question number 2. Question number 2. Just put some replies. This idea clear. Put some reply in the YouTube chat. This idea clear. Put some reply in the YouTube chat. This idea clear. Put some reply in the YouTube chat. Reply soon. Clear, right? Not difficult, very clear and simple. So next one. Figure shows two wave pulses traveling in opposite directions along a straight string. Which of the following diagrams best represents the shape of the pulses in the subsequent motion after they meet together? Now, before story, just before they have given two pulses in two different shapes. Right, before. The two pulses are in two different shapes. The two pulses are in two different shapes. Okay, right. This pulse propagates to the right and this pulse propagates to the left before. Now after also now at the moment when these two pulses superimpose on each other, there will be an overall change in the resultant wave pulse. During the moment both the pulses superimpose on each other, we can clearly see a difference in the resultant pulse shape. But after some time later, this pulse keeps on moving left side, this pulse keeps on moving right side. Now they haven't mentioned, now based on this given diagram very clear, now they mentioned what? They're asking which of the following diagrams best represents the shape of the pulses, the subsequent motion after they meet together. They are not talking anything about during they meet together. During they meet together, the shape of the resultant pulse is somewhat different than both these shapes. But after they meet each other, we don't see any difference in the shape of the pulses. This pulse will be at the left side. It further moves to the left side. This pulse will be at the right side. It further moves to the right side. That is the idea. If I do after scenario, after scenario, after scenario, after this pulse will be moving right side. Okay. This pulse will moving. This pulse will move to the left side. Not difficult if you learn properly basic questions. The allocated, you should take around 2 to 3 seconds to get the answer. After. Then that question also clear. Now question number 3, next story. Figure shows the instantaneous position of a transverse wave traveling to the right on a water surface. A and B are two small floating objects. A and B are two small floating objects. As the wave travels away from this position to the right, both A and B will begin to move right, both A and B begin to move left. They have given some options. Right, that story, that question is really important because most of the MCQs, this type of questions they ask frequently. 1997 level question. 1997 level question. I told you, okay, I will tell you some stories. 1997 level question. 1997 level question. This idea. Right? I'll draw the wave. Then I'll explain. Okay? Question number 3. Number 3. Right, listen very carefully. Okay. Right. Okay. Right. Okay. Please write every important theory point. Every discussion completes. If you feel something is important, immediately take your short note point book and write all the important points. Write all the important points. Keep it as a habit. Okay, write me. Now listen to the idea very carefully. Now this is a water wave propagating on the surface of the water. Now they mentioned two particles on the water surface, right? You can assume there are two particles floating on the water surface. So you can consider two particles as two water particles and you can understand what will happen, right? One can think there are two objects on the water surface. If not, you can consider point capital A and point capital B are two water particles, right? Now this is a water wave propagation, therefore medium particles are going to be water particles. Just assume point capital A and point capital B as two water particles. Since it's a transverse wave propagation, we all know that. What is the important story? If it is a transverse wave propagation, we know medium particles oscillate, vibrate perpendicular to the wave propagation. Now very clearly they mentioned that wave is propagated to the right side direction. Wave is propagated to the right side direction. Very clearly they mentioned that idea. Then we all know that. So when the wave propagates right side direction, the medium particles, that means the water particles, should propagate perpendicular to the wave propagation. That means all the water particles are moving vertically up and down. Especially I told you that each water particle is following a simple harmonic motion. That story I explained already in the theory classes. Now you want to understand the next instant. Now at t equals 0, let's say now this moment when you freeze the water wave, at this moment when t equals 0, water particle at A and water particle B are at these two locations. Right? This water particle A and water particle B are at this location. They are asking in the next instant, because we know the wave propagates to the right side direction. The next instant, where would be the locations of these two water particles A and B? I told you that in such cases, I told you, if you can remember, draw the next instant of the wave. Draw the next instant of the wave. Then you will be able to identify the location of water particle A and B easily at the next instant. Theory classes, I taught this idea. Okay, if I do the next instant of this water wave propagation, the next instant, I will draw in blue color. If I draw in blue color, the next instant, the wave front going to be. Okay. Okay. Right. Okay. This black color dotted wave belongs to location of the wave at t equals 0. This blue color wave is the location of the wave with the time is t equals simply something. So what we realized is, I told you, all the medium particles should oscillate perpendicular to the wave propagation. That means the medium particle water particle A can oscillate up and down only. Since it's a transverse wave, the water particle at A, the water particle at any location can oscillate perpendicular direction only. In that case, the next instant, where would be the water particle A? Water particle A would be in the upward direction, upward at this location. This water particle A would be exactly at this location. So water particle A is moving upwards. What will happen for the water particle B? The next instant we notice water particle B would move down direction. And individually you want to understand water particle A and particle B, they move in simple harmonic motion, perpendicular direction to the wave propagation. If I consider water particle A's oscillation, right? Water particle A moves in a vertical simple harmonic motion, SHM. Then very clear. Now question is very clear. If you draw the next instant of the wave propagation, you will be easily able to identify the location of medium particles. Now with the question what they are asking, in the question they are asking, figure shows the instantaneous position of a transverse wave traveling to the right on a water surface A and B are two small floating objects. Don't think them as objects, think A and B as two water particles. As the wave travels away from the position to the right, wave is propagating right side direction. Now we understand. A begins to move upwards, seriously. The next instant, A begins to move upwards. Water particle A, if not object A, begins to move upwards. That's correct. And what about the B? B begins to move downwards. A begins to move upwards and B begins to move downwards. Therefore, question number 3 answer is fourth one. So these are not time-consuming MCQs. Within maximum 30 seconds, you should be able to get the answer. Even 30 seconds is also too much, right? In the given paper itself, you should know the next instant of the wave. Then you should mark the next locations of particle A and B. Question number 4 is very simple. Which of the following which of the following waveforms has the highest frequency? Now very clearly, look, they have given the diagrams. 1990, haven't mentioned the year. Most probably it should be 1990 80 level MCQ. Next idea. Next story. Okay. 1990 level question. MCQ. Number 4. Which of the following waveforms has the highest frequency? We know that. We know now. We can clearly see now. Larger the wavelength, right? According to V equals F lambda equation, adjusting velocity, speed is constant. Larger the wavelength results smaller frequency. Smaller the wavelength will result larger frequency. Now you can clearly see that in this scenario, which diagram shows smaller frequency? According to V equals F lambda equation. According to V equals F lambda equation, if you assume speed of the wave remains constant in the relevant medium, larger the wavelength results smaller frequency. When your wavelength is smaller, the respective frequency will be larger. Then tell me, out of those 5 given diagrams, which diagram shows smaller wavelength? Very clear, option number 5. Since option number 5 shows the smaller wavelength, its frequency must be larger, right? Because I think you all can remember this idea. I hope you guys are aware what does it mean by wavelength. There are lots of definitions for wavelength. The distance between 2 adjacent crests or troughs, if not the distance between 2 adjacent compressions or refractions, if not length of one complete wave cycle. Length of one complete wave cycle we defined as wavelength. If not, the distance between 2 adjacent medium particles under same phase. There are different definitions for wavelength. Right? Length of one complete cycle is, we can call it as wavelength. If you consider one cycle, this length is, we can call it as wavelength. Right? This story. Many will forget the definition for wavelength like this. The distance between 2 adjacent medium particles under same phase is also, we can define as wavelength. Many will forget that story. Most of you can remember, so wavelength means the distance between 2 adjacent crests, 2 adjacent troughs, 2 adjacent compressions, refractions. Many can remember those stories. But the most important stories, many will forget easily. But you want to remember wavelength means one complete cycle length, if not distance between 2 adjacent medium particles under same phase. Right? This story also put in your short note point book. When you consider 2 medium particles adjacent, medium particles vibrating under same phase, what is the phase difference between them? 360. Right? If the 2 medium particles are vibrating under same phase, the phase difference between them is equal to 360. That story also keep in your mind, that idea. Right, simply, question number 4 also done, 5 story. Fifth one idea. Right, as shown in the figure, 2 pulses of identical shape with amplitude 2 centimeter, are traveling along a string in opposite directions. All right. With the same speed, 2 centimeter per second, if the pulses are 8 centimeter apart initially, wave pattern after 2 seconds is given by. This story. Not difficult. 1999 A-level question. 1999 A-level question, not difficult, can do. right? Question number 5. Now there are two pulses, but both are they are moving in opposite directions. Both the pulses are moving towards each other, but we can clearly see that there's a phase difference between them, 180-degree phase difference between them. Okay, there are two pulses, seem like it has same amplitude, both the pulses moving under same speed, but there's a phase difference between both the pulses. What is the phase difference between both the pulses? 180-degree. That story put in your mind. Short note point book also include. Right. Okay. Not difficult. Can do. Okay, can do. This pulse moves to the right side with velocity 2 centimeter per second. 2 centimeter per second. And also this pulse moves to the left side. The speed of 2 centimeter per second. Okay, right. They mentioned when t equals 0, the gap between these two pulses is 8 centimeter. When t equals 0, the gap between these two pulses is 8 centimeter. I draw vertical line. Look here. Learn things properly, then everything is easy. Everything is easy. Okay. Right. Okay. This gap is 8 centimeter. When t equals 0. Okay. Right. Okay. Now, when the time is 2 seconds, they're asking if the pulses are 8 centimeter apart initially, wave pattern after 2 seconds in the given by. After 2 seconds, what would be the resultant wave pattern? That is what they ask. First of all, we'll check what will happen. Exactly the time is 2 seconds, we'll identify where will be this pulse and where will be this pulse at 2 seconds. At 2 seconds. Right? Right? Okay. Right. Then I consider now this is the center line passing through 8 centimeter. That means gap is 4 centimeter, 4 centimeter. The gap between these two vertical lines is 8 centimeter. This is a center line. That means this gap is 4 centimeter and this gap is also should be 4 centimeter. 4 centimeter, 4 centimeter. Now tell me now, we'll talk about this pulse. Within 2 seconds, when the time is 2 seconds, where will be this pulse? We know the speed of the pulse. And if I know the speed of the pulse and time taken is 2 seconds, we can find the distance traveled by this pulse. I need this pulse as pulse number 1. This pulse is pulse number 2. For the pulse number 1, if you apply the basic equation S equals ut to find the distance traveled by that pulse number 1, apply. For the pulse number 1, if you apply the basic equation S equals ut, get the answer. S equals ut, then I want to find the distance traveled by the pulse number 1, that is something. Speed of the pulse is 2 centimeter per second, 2 centimeter per second, time taken is 2 seconds, 4 centimeters. right? When you apply S equals ut, then where is the pulse number 1? Okay. Distance traveled by the pulse number 1 within 2-second time period is 4 centimeter. Then where will be pulse number 1? When t equals 0, pulse number 1 is here. The time is 2 seconds. Where will be pulse number 1? Pulse number 1 will be exactly at this location. Right? So pulse number 1. This gap is 4 centimeter. This gap is also 4 centimeter. Then tell me where will be the pulse number 2? When t equals 2 seconds, where will be pulse number 2? So you can apply S equals ut equation for pulse number 2 also. Right, okay, we'll apply it. It's not necessary. Right, even when you're doing the MCQ, you don't want to apply S equals ut. Right, this part should be done by your heart. Right, you should not take time to find the distance traveled by pulse number 1 and pulse number 2. Don't apply any equations and don't find it. Basic story is equals ut. Now very clear, pulse number 1, pulse number 2, both of them move towards each other under uniform velocities. Therefore, only equation is equals ut. Within 2 second distance traveled by pulse number 1 is 4 centimeter. That part, please don't try to do in the paper. You can do in yourself. You can do by your mind. Try to improve your mind to that level. That's important. Then when I'm explaining, I'm following the steps, but you don't follow those steps when you're doing the question. Now, if I apply the same equation for pulse number 2 also, S equals ut equation, left side direction. Then distance traveled by pulse number 2 also same as 4 centimeter. Speed of the pulse number 2 is 2. Time taken is 2 seconds. 4 centimeter. 4 centimeter. 4 centimeter. Right? Then if I mark the location of the pulse number 2 at 2 second time period, I'm marking right. Pulse number 2 will be exactly this. Then very simple. The very simple story, sir. Very simple thing. Then ratio, now we don't have a Zoom session. Then very clear, what is the result? But they're asking if the pulses are 8 centimeter apart initially, wave pattern after 2 seconds is given by. Answer is 5. Because during the superposition between these two pulses, it's a destructive interference happens between these two pulses. Not constructive. It's a destructive interference occurs between these two pulses. The result is what? A horizontal line. Right? It appears like a horizontal line. At this moment, okay? At 2 second moment, you can see only a horizontal line. So therefore the answer is what? Fifth one. You can see a horizontal line. At 2 second exactly, you can see a horizontal line. Nice question. Nice question. Learn something from this question. Right? Nice story. Next story. Next story. Then question number 6. 2011 not difficult. Next story. 2000 A level. 2000 A level question is not difficult. Easy question only. 2000 A level. Question number 6. Right. They are saying what? Question says that transverse pulse, okay, traveling on a stretched string as shown in the figure. Right, stretched string. The left end of the string is tied to a light ring that could slide on a frictionless rod perpendicular to the string. Then this story, that is a kind of soft boundary. Right, then soft reflection occurs at the boundary. This theory part we learned in our theory classes. Okay, right. The reflected pulse is best represented by simple, right? Simple. Okay. Now there is a diagram missing. I think diagram is missing. Okay, small diagram is missing in that question. Diagram is missing. Do you have any Pesuru, any PDF? If you have any Pesuru PDF. This question, if someone have the Pesuru PDF, I can't find it now. If someone have, can someone quickly send a picture of this question number 6 soon? Then we can quickly work on it. Anyone? Anyone? This question, right? Okay, thank you, Maya. Thank you. Right. Now the given diagram is okay. The given diagram is like this, ni? Okay. This given diagram. The given diagram is just before the reflection. The ring. If I draw the wave pulse, it's going to be like this. This wave pulse moving towards left side. Right, this is the soft boundary, because why? The raw particles are able to vibrate freely up and down. Therefore, this end is a soft boundary. As a result, soft reflection occurs at this boundary. Soft boundary. Then if I draw the reflected wave pulse, there won't be any 180-degree phase difference. Reflected pulse won't be inverted. If I do the reflected wave pulse, it's going to be like this. It's going to be like this. Like this. This is the incident pulse. This incident pulse undergoes soft reflection at the soft boundary. Then the reflected pulse going to be like this. So we can clearly see that there is no phase difference of 180-degree. If not, reflected pulse is not inverted. So we can clearly see a non-inverted reflected pulse. That question, therefore, answer is, I think second one is the answer. This question answer is second one. Right? Second one is the answer. Okay. Next idea. 6 done. 6 done. Next story. Next theory. Next question. Then 7th one we'll discuss in a while. We'll discuss in a while 7th one. Question number 8. 8th one. Consider the following statements made regarding longitudinal and transverse waves. Only transverse wave can undergo refraction. That's wrong. Statement A is wrong. Question number 8. Question number 8. 2003 A-level question. 2003 A-level question. 2003 A-level question. Question number 8. Statement A, B, C. There are 3 statements A, B, C. Statement A says that only transverse wave can undergo refraction. No. Right. Even the longitudinal waves also can undergo refraction, reflection, interference, diffraction. But when you consider longitudinal waves, they don't undergo polarization. But transverse waves, they undergo polarization. Right? So therefore, statement A is wrong. Only transverse waves can undergo refraction. Wrong. Statement A is wrong. Statement B. B says that both types of waves can undergo interference and diffraction. Correct. B is correct. Both types of waves can produce beats. Correct. Both types of waves can produce beats. Correct. Therefore, A is wrong. B and C correct. Therefore, answer is 4th one. Right? Question number 9. 9th one story. Question number 9, 2004 A-level question. 2004 A-level question. Idea? Two strings A and B are connected end to end at point capital P. Two strings A and B are connected end to end at point capital P as shown in the figure. Right? And the free end of the lighter string B, I think the string B is lighter. Okay, free end of the lighter string B is attached to a rigid vertical wall. Then what I understand is string A is heavier string and string B is lighter string. Okay. The mass per unit length of A and B are 0.04 kilogram per meter and 0.01 kilogram per meter respectively. The composite string is first pulled by hand to create a tension of 1 Newton, and then a pulse is created at the free end of A after the pulse has reached the point capital P. After the pulse has reached the point capital P. Okay. Right? Okay. Okay. Right. See this idea? This story. Now this theory part is also I explained in my theory classes. Now when you connect when you connect heavy string and a light string, how the wave pulse propagates in the heavier and lighter strings. That's theory story we learned already. Once again. See this idea? Once again. Okay. Once again. Okay. This is string A. It is heavier. It's heavy. It's heavy. It's heavy. Right? If I draw the wave pulse propagating to the right side, the wave pulse. Okay, right side. String A. And if I draw the lighter string B, string B. One end is attached to the heavier string, other end of the light string is attached to the vertical wall something. Okay. String B is light. Okay. Now they have given the linear density of string A and string B. They have given tension is 1 Newton. Important theory points, remember now, important theory point is when two strings are attached in series, this heavy string as well as light string is attached in series. In that case, remember the tension force acting on both strings are same. Okay. If they mention tension force on heavy string is 1 Newton, remember tension force on the light string also same as 1 Newton. Same tension. The strings in series have same tension. That story. And also we can remember what is the equation we learn to find the velocity of a transverse wave propagating in a straight string? The equation is V equals capital T over simple M whole root. Then when this wave pulse propagating in the lighter string, they have mentioned linear density of lighter string is how much? 0.01 kilogram per meter. Given data. Okay. Simple MB means what? Linear density of string B. That is 0.01 kilogram per meter. Then we can easily find the velocity of the wave pulse propagating on the lighter string. Tension 1 Newton. Linear density of the lighter string is 0.01. What is the velocity of the wave pulse propagating in the lighter string? Substitution. For the string B, for lighter string, velocity going to be, tension is 1 Newton, linear density is how much? 0.01 whole root. When you simplify, it's going to be 0.1 or 0.01 means 100. Root 100 means, remember, it's 10 ms minus 1. 10 ms minus 1, that is going to be the velocity. And also, what about sir now at this point? This point, let's take it as point capital P. What do you think about point capital P? Is it a soft reflection happened? So is it a soft boundary or a rough boundary? If it is boundary, point capital P is a soft boundary or is it a rigid boundary? Remember, if the wave pulse propagating from heaviest string to the lightest string, point capital B going to be a soft boundary. Suppose the wave pulse is propagating from lightest string to the heaviest string, point capital B going to be a rigid boundary. Do you understand? If the wave pulse propagating initially from heaviest string to lightest string, point capital B connecting point going to be a soft boundary. Suppose if the pulse is propagating from lightest string to heaviest string, then point capital B going to be a rigid boundary. And now since the wave pulse propagating from heaviest string to the lightest string, this point capital B going to be a soft boundary. Point capital B is a soft boundary. Soft boundary. If it is soft boundary, we all know that there won't be any inversion. The reflected wave pulse won't be inverted. Right? The reflected wave pulse won't be inverted. Soft boundary. So therefore, if I do the reflected wave pulse also passing through point capital B, it's going to be like this. The reflected wave pulse won't be inverted. That's what I want to mention. Do you understand? Do you understand this story? This idea as well as I should draw the reflected wave pulse at here is also I want to draw it. Right? Now this is the incident wave pulse. At this soft boundary, if I draw the reflected wave pulse, it's going to be like this. If I draw it properly, okay, I'll draw this below diagram. If I draw this story in below diagram, that's better. Okay. Also, I find the velocity of transverse wave propagating in the stretch string also. I'll find the velocity of transverse wave propagating in string A also, heavy string also. Then capital A going to be how much? Capital A going to be velocity of the transverse wave propagating in the heavy string is capital T over simple M. Tension force is 1. Linear density of heavy string is 0.04. 0.04. 1 over 0.04 whole root. So therefore, I can write on V as what? 25 root. 1 over 0.04 means remember 25 root. Okay. Now simplify. 1 over 0.04 means remember just do a calculation and check. It's 25. 25 root is remember 5 ms minus 1. 5 ms minus 1. So if I draw the reflected wave pulses after reflecting from the soft boundary, it would be like this. It would be like this. Look here. This is point capital P. This is the vertical wall. Now, before the wave pulse propagating through the heaviest string reaching the soft boundary. After reflecting from soft boundary, reflected wave is not inverted. Reflected wave pulse is not inverted. If I draw the reflected wave pulse propagating to the heavy string, it's going to be like this. It's going to be like this. Reflected wave pulse. It's going to be like this. Right? Reflected wave pulse is not inverted, going backwards. What is the speed of the reflected wave pulse? That is how much? That is 5 ms minus 1. 5 ms minus 1. Also, if you can remember, I explained that during the reflection, small wave pulse propagates through the light string also. Right? Just after the reflection and the soft boundary, a small wave pulse propagating through the light string also. A small wave pulse. This small wave pulse propagates to the right side direction. This small wave pulse propagates to the right side direction with a speed of 10 ms minus 1. This is the overall idea. Overall idea. But they are asking, what they are asking in the question they are asking that two strings A and B are connected end to end at point capital P as shown in the figure. And the free end of the lighter string B is attached to a rigid vertical wall. The masses per unit length of A and B are 0.04 and 0.01 respectively. The composite string is first pulled by hand to create a tension, pulled by hand to create a tension of 1 Newton, and then a pulse is created at the free end of A. After the pulse has reached the point capital P, then non-inverted, option 1 is what? Non-inverted pulse would have travelled along B to the right side with a speed of 10 ms minus 1. Non-inverted pulse would have travelled along B to the right with a speed of 10 ms minus 1. Okay, we'll keep that, option number 2. An inverted pulse would have travelled along B to the right with a speed of 10. Option number 3, non-inverted pulse would have travelled to the left along A with a speed of 10 ms minus 1. An uninverted, okay, that is also wrong, okay. An inverted pulse would have travelled, that's definitely wrong. No pulse would have travelled along A to the left, wrong, okay. What is the right answer? Right answer. Option 4 and option 5 definitely wrong. We talked this story in the theory classes. If there is a heavier string attached to a lighter string, and initially if the wave pulse propagates through the heavier string, this point capital P is going to be a soft boundary, therefore soft reflection occurs at point capital P. Just after reflection, what will happen? This wave pulse reflects back without any inversion. Reflected wave is a non-inverted wavefront. Reflected wavefront is a non-inverted wavefront. This is the V. And also I told you that just after reflection at point capital P, there's a small wave pulse propagating through the lighter string also to the right side direction. Okay, and now option 4, option 5 is wrong. Option 1, 2, 3. Option 1, non-inverted pulse would have travelled along B to the right side with a velocity of 10 ms minus 1. It is correct. Option 1 is correct. Option 2, inverted pulse, wrong. Because after reflection, we don't see any inverted pulses. Option 2 is wrong. Option 3, non-inverted pulse would have travelled to the left. That is correct. Non-inverted pulse would have travelled to the left. That is correct, along a speed of 10. But this non-inverted pulse travelling along string A at a speed of 5, not 10. This one is travelling at a speed of 5. This pulse is travelling at a speed of 10. Therefore, the right answer is option 1. Option 1 is the right answer. Put some replies. Till now, all clear, put some reply. 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 Put some reply. All clear, put some reply. Put some reply. Till now, if it is clear, all clear, put some reply. Put some reply. Put some reply in the chat. If all clear, put some reply. Put some reply. Remember, this is not for 27 students. This is 26 past paper class, past paper discussion. Therefore, 27 batch students, they don't want to stay in the session. No need, okay? Right, all clear, all simple, very simple story. If you learn properly, everything is simple. Right, all clear. Next story, few more questions there, then finish story. Then we are starting optics past paper discussion also. Next idea. We'll go to any easy questions. Any easy questions? I think question number 10. 2005 A-level is also not difficult. Figure shows two identical pulses moving towards each other along a string. The two instances where simply two pulses overlap completely. Simple B, sometime after. The overlapping occurs are best represented by. During they superimpose on each other, what would be the resultant pulse shape? After some time later, what would be the shape of the pulses? That's what they ask. Now, anyone will understand. Okay, I will do the diagram. 2005 A-level question. 2005 A-level question. Look here. This story. 2005 A-level question. There are two identical wave pulses propagating towards each other with same phase. There are two non-inverted pulses propagating towards each other and the same speed, and just think both the pulses are identical, having same amplitude, moving towards each other and the same velocity. Think like that, then easy. Then easy. Question number 10, I think. Question number 10, I think. This pulse moves to the right side and this pulse moving to the left side. Now understand both of them are identical wave pulses, therefore both of them have same amplitude and both of them move towards each other at the same speed, thing like that. Then we learned when the moment both the pulses superimpose on each other, what can you say about the amplitude of the resultant pulse? Twice the amplitude of each pulse. If you say amplitude of each pulse is capital A, capital E, amplitude capital E. Both of them have same amplitude capital E before the superimposition. During superposition, the shape of the resultant pulse is going to be twice the amplitude. The shape of the resultant wave pulse is going to be twice the amplitude. 2 capital E. 2 capital E. During the superposition, sometime later from the superposition of the pulses, if you know the shape of the two wave fronts, it's going to be like this. It's going to be like this. It's going to be like this. Same one, this one is already at the left side, moving further to the left side. This one is in the right side and moving further to the right side direction. Simple story. Not difficult stories. If you learn properly, everything is simple. Learn properly, everything is going to be simple. This pulse will be at the left side, moving further to the right side. This pulse will be at the right side and moving further in the right side direction. That is the idea. Clearly? This is the idea. Clearly? Simple story. Then what is the right answer? That question number 10, the right answer going to be what? It's going to be, right answer going to be same like second one. First one is wrong, then third one, fourth one wrong, fifth one also wrong. Therefore the right answer going to be option number 2 is the answer, right answer. Second one is the right answer. Very simple question. 11. As a mechanical wave propagates in a medium, the energy of the wave dissipates gradually. Right? As a mechanical wave propagates in a medium, the energy of the wave dissipates gradually. This will gradually, remember there is a connection between amplitude and energy of a wave. When the energy of the wave decreases, put in your mind, amplitude of that wave also decreases. Do you understand? If the energy of a wave decreases, its amplitude also decreases. As a mechanical wave propagates in a medium, the energy of the wave dissipates gradually. This will gradually, option 1, decrease the speed of the wave, decrease the frequency, no, wrong. Decrease the amplitude of the wave. Answer is option number 2. Option number 2. When wave's energy decreases, its amplitude decreases. Nothing will happen for the frequency of wavelength to velocity. Right? Question number 11, answer is second one, very basic question. 2006 level question. That is simple. That is simple. 2006 A level question. The answer going to be how much? It's going to be second one. Question number 11. Answer is second one. Next idea. Question number 11 done. 12 S-wave story. 12 not difficult. 12, 13, then 14, 15. In easy questions. 15 is easy. 15 is easy. A symmetrical pulse showed in the figure is moving along a string towards a rigid boundary. Which of the following figures correctly shows the resultant pulse at the instant when exactly half of the pulse is reflected from the rigid boundary? This story I explained in detail in theory classes. Right? Okay. Question number 15, 2008 level question. This past paper discussion is kind of a quick revision. What you learned in your theory classes. Right. 2008 A-level question. 2008 A-level question. Okay. 15. Right. 15 vertical wall. Okay. Right. Now we know that since this string is attached to the vertical wall rigidly, this point going to be a rigid boundary. Then we know rigid reflection occurs at this point, at this boundary, rigid reflection will occur. Okay, right. Then we learned, if you can remember, now they are saying that which of the following figure correctly shows the resultant pulse at the instant when exactly half of the pulse is reflected from the rigid boundary. I told you that only half of the pulse has reached the rigid boundary. The remaining half yet to reach the rigid boundary. If I do the pulse in larger way, look here. This is your wave pulse reaching the boundary. Only half of the pulse is reached. Only this half of the pulse is reached the rigid boundary and this half of the pulse inverted. If I read my bad. Only first half of the pulse is reached the rigid boundary. Only first half of the pulse is reached the rigid boundary and first half is reflected from the rigid boundary. Then we know in a rigid boundary, if rigid reflection occurs, what will happen to the wave pulse? Wave pulse will be inverted. In that case, when you consider this wave pulse is reaching the boundary, the first half of the pulse already reached the boundary. First half of the pulse will undergo inverted reflected pulse. There will be a inverted reflected pulse. If I do the shape of the reflected pulse, it's going to be like this. It's going to be like this. It's going to be like this. Okay. This is going to be the reflected pulse. Clear? Now please don't you miss this idea, very basic idea. There is an incident wave pulse. It's propagating towards the rigid boundary. Right? If only half of the wave pulse reach the rigid boundary, that means if only this half of the wave pulse reach the rigid boundary, it will reflect But we know reflected pulse has a inverted, there will be an inverted reflected pulse. There will be an inverted reflected pulse. This is going to be that inverted reflected wave pulse. But still remaining half of the incident pulse yet to reach the boundary. The remaining half of the wave pulse, the remaining half of the incident wave pulse yet to reach the boundary. As a result, what can you say about the resultant shape of the wave pulse? The resultant shape of the wave pulse is going to be what? You can see something, a horizontal shape in the string. You can't see any wave pulse during that moment. For a small instant, you see the wave is disappeared. For a small instant, you will see that wave pulse is disappeared. For a small instant, you will see that wave pulse is disappeared. For a small instant. Very simple question. 15 answer is going to be, I think, fifth one is the answer. Then then question number 16 we'll discuss later. 17. Okay, 17, 18, 19, 20, 21. Okay, question number, we'll go to 17. 2010 year question. 17. The figure shows a wave pulse traveling along a string towards its end, which is connected to a small light ring that can move along a vertical wire. Then we know that the string, since the string is attached to a small ring, that ring is able to move up and down along that rod. That end of the string is going to be a soft boundary. That end is going to be a soft boundary, that story. Okay. Which of the following figures best represents the shape of the wave pulse at the instant when the peak of the pulse reaches the ring? That means they are telling if the half of the wave pulse reached the boundary, what would be the shape of the resultant pulse? Do you understand? If the half of the wave pulse reached the boundary, what would be the shape of the resultant pulse? If it is a rigid boundary, if it is a rigid reflection, we notice that if half of the wave pulse reaches the rigid boundary, we can't see any wave pulse in the string. For a small instant, wave pulse disappears. But if it is a soft boundary, and if half of the wave pulse reaches the soft boundary, what would be the shape of the resultant wave pulse? Remember, we learned resultant wave pulse will be twice. Okay, I told you that the amplitude of the resultant wave pulse will be twice than incident wave pulse amplitude. Okay, that idea. Okay, that idea. The stories I explained. During a soft boundary, during a soft reflection, what happens? If the half of the incident wave pulse reaches the soft boundary, the resultant wave pulse will have an amplitude twice the amplitude of incident wave pulse amplitude. Okay? We learn this idea. These stories we learned. Let's say incident wave pulse having amplitude capital E. It is having amplitude capital E. When the half of the incident pulse reaches the soft boundary, we can see a resultant pulse having amplitude twice the amplitude of incident wave pulse. That theory we learned. If I do that instant, okay, when the half of the incident pulse reaches the soft boundary, the resultant wave pulse has an amplitude twice the amplitude of incident wave pulse. It's going to be 2 capital E. These are tiny points that you want to remember. But theory classes we learned, I taught every theory point properly. Therefore, anyone can able to get The answers, not difficult. Are these past paper questions are difficult? Are these difficult? It's not difficult. If you properly practice the papers, if you really have the oral exposed about past papers from 1992, 2025 A level, no one can, you must get A. Right? If you have the oral exposed about the past papers for the last 35 years of past papers, they can't do a big magic. They can't give us something very difficult paper in your AL exam. Right? I'm talking about AL exam paper. Definitely they want to take an approach about the previous papers. They want to take some previous past paper questions as the reference questions and they want to prepare a paper. Since you already, you've done, you tried many times, 35 years of papers, then your ALL paper is not going to be a paper for you. It's going to be one of the past paper for you. Even your ALL paper is also going to be one of your past paper for you. If you practice properly. Okay, that idea. I think that's also done. Nice story. Nice story. Time is 8 o'clock. We are taking a break at 9:15. First break is at 9:15. That question, 2010 year question, very clear. What is the answer? Soft boundary. Soft boundary means we don't see any inverted wave fronts. Soft boundary means this is the diagram. Therefore, question number 17 answer is going to be second one is the answer. 18 easy. 18, which of the following waves require a physical medium for traveling? Mechanical waves only require physical medium to travel. But we know electromagnetic waves, they don't require a physical medium. Here, light wave is electromagnetic wave, radio electromagnetic. Sound is a mechanical wave, which is a longitudinal wave. Therefore, answer is third one. Question number 19, which of the following propagates in the form of longitudinal waves? Ultrasonic waves, not ultraviolet. Ultrasonic wave is basically a sound wave. All sound waves are longitudinal waves. Third one is the answer. Which of the following statement made regarding seismic waves is incorrect? Seismic wave stories we learned, right? We learned seismic wave story. Question number 18 done, 19 done, 20. Which of the following statements made regarding seismic waves is incorrect? Incorrect. All seismic waves are mechanical waves and require a medium to propagate. That is correct. All seismic waves are mechanical waves. They require a medium to propagate. That's correct. Right? Okay. Because under our syllabus, we talk only the electromagnetic waves which do not require a medium to propagate. Other than electromagnetic waves, all the waves that we talk in our syllabus require a medium to propagate. Even the sound, even the seismic waves, and the transverse wave propagating a straight stream. All of them require a medium. So therefore, incorrectly, option 1 is correct. Option number 2, primary waves are longitudinal and secondary waves are transverse. That story will keep. Option number 3, speed of secondary wave is less than the speed of secondary wave is S means secondary wave. Speed of secondary wave is less than that of P wave. P means primary. So we know that primary waves has large speed than secondary waves. Therefore, option number 3 is also correct. Fourth option. As secondary waves can travel through both liquids and solid media. Right, secondary waves can travel through both liquid and solid media. That story. Primary waves can travel through both liquid and solid media. We learn these ideas properly. We learned. Tell me what is the right answer. Question number 20. Reply everyone. Put some replies. What is the right answer for question number 20? We learned this idea. Everyone put a reply. What is the right answer for question number 20? We learned. This story we learned. Everyone put a reply. What is the right answer? Reply everyone. What should be the right answer? Reply everyone. Reply everyone. What should be the right answer? Reply everyone. What should be the right answer? Reply everyone. Quickly soon. Reply everyone. What should be the right answer? Everyone reply soon. So no time. Then we have few more questions. Then entire tutor is fully finished. Huh? Reply everyone quickly. What must be the right answer? What must be the right answer? Reply everyone. Reply everyone. What must be the right answer? Reply everyone. Anyone responding? Reply everyone. Reply everyone. Anyone can tell me the answer. It's not difficult question. It's learn by heart story. Not a difficult question. Anyone can tell. Anyone can tell. It's learn by heart story, not a difficult question. Not a difficult question. Anyone can tell. Right? Anyone can tell the answer. Anyone can tell the answer. That story. That's not difficult. You guys can tell me the answer. That story also done. Then we discuss 18, 19, 20. We have done 17 done. 16 story we want to discuss. Question number 21 story. 21 idea. 21. Right. 21 2020 question. Positions of particles of transverse wave traveling along x direction. Positions of particles of a transverse wave traveling along x direction at a certain instant is shown in the figure. A pair of particles with same instantaneous velocities. A pair of particles with same instantaneous velocities. Pair of particles. Same instantaneous velocities. This story I will explain properly. Many have a problem regarding these stories. Okay, I will explain this idea. Instantaneous velocities. If I explain this idea, very carefully listen. Very important question. Very important question. Everyone listen very carefully. Very carefully listen. Okay. Right. All right. All right. Question number 21. Question 21. 2020 A-level question. 2020 A-level question. 2020 A-level question. Number 21. Okay. Right. Question number 21. Right. I will draw the waveform. If I draw the waveform, somewhat okay. Okay, listen. And also now this wave is propagating in the right side direction. If I draw the next instant of this wave, if I draw in blue color, the next instant of this wave, here's the wave moves right side. Okay. Right. Now I will mark the location of some medium particles A, B, C, D, E. Medium particles. Right, medium particles A, B, C, D, E, F. A, B, C, D, E, F, medium particles. I should draw a larger diagram, I think. Okay, right. Medium particle A. Here is our medium particle A, I guess. And medium particle B going to be somewhere here. And if I draw medium particle C, that is somewhere here, medium particle C. Medium particle D will be somewhere here. And medium particle E is somewhere here. And then medium particle F will be somewhere here. Medium particle F. Right. Then shall we mark the now? In the next instant, shall we mark the location of in the next instant? Now A, B, C, D, E, there are A, B, C, D, E, F. There are 6 medium particles. When t equals 0, these are the locations of these 6 medium particles. Thing like that. In the next instant, if I mark the location of those medium particles A, B, C, D, E, F, the next instant, right? Very clear, this medium particle A moves downwards. The next instant, this medium particle A moves down. medium particle A moves down the next instant. Medium particle A moves downwards. What about the medium particle B that is also moving downwards? Medium particle C seems like moving upwards. Medium particle D also moves upward. Medium particle E that is also moving upwards in the next instant. Medium particle F is moving downwards, right? Now they are asking what in the question? In the question they are asking positions of particles of a transverse wave traveling along x direction at a certain instance is shown in the figure. A pair of particles with same instantaneous velocities. Pair of particles having same instantaneous velocities. Okay. Right. B and F. Particle B, particle F. Now B and F, both of them have same direction. Right? B as well as particle F, both of them are moving downwards in the next instant. We'll check about the direction of their velocities are same. When you consider particle B and F, the next instant both particle B and F move downwards. Directional velocity of them are downwards, no doubt. But we'll come to a judgment regarding their velocities in a while. Okay, we'll talk about the velocities in a while. Okay. Second option, A and D. A and D, remember, now point A, particle A goes down, particle D goes up. Therefore, particle A and particle D have different velocity directions. Now they are asking same instantaneous velocity. Magnitude as well as direction of the velocity must be same. If you consider particle A and particle D, since both of them move in opposite directions, particle A moves down in the next instant, particle B moves upwards in the next instant. Therefore, remember, particle A and D have different directions of velocities. Therefore, option 2 can't be. If both of them have same velocity, both of them should have same direction. But particle A and particle D have velocities in different directions, opposite directions. Therefore, second option can't be. B and C. B is moving downwards, C is moving upwards. Therefore, option number 3 also can't be. C and F. C and F. C is going upwards, F is going downwards. That case also can't be. Then B and E. Option B, B is moving downwards, E is moving upward. In that case also, it can't be. Therefore, the right answer is, I feel like option B and F. B and F, that is going to be the right answer. Because velocity B and F medium particles have same velocity direction the next instant. But one can argue that's just because their directions are same. What about their magnitudes? If we know the simple harmonic motion theory, right? Just consider this is the equilibrium point, okay? If I draw this particle B and particle F in the same vertical line, okay? If I draw the particle B and particle F, same vertical line in simple harmonic motion, vertical simple harmonic motion. Vertical simple harmonic motion. Equilibrium level, this is the equilibrium level, this level. Equilibrium level, this level. Okay, right. And then if I draw the particle B somewhere here, this is the particle B. And when you carefully check the particle F and particle B, the displacement magnitude from the equilibrium point to particle B and the displacement from equilibrium point to particle F are same. This gap and this gap same. Then simple harmonic motion, you all know that when the gap is same, at same displacements, they will have same velocity. You can use the equation also. V squared equals what? V squared equals omega squared capital A squared minus x squared. That equation also you can apply. Same displacements, remember, same magnitude of velocity. But different same displacements, remember, same magnitude of velocity. Simple x. This capital simple x. This capital same displacement means same magnitude of velocity obtained by particle B and particle F at this location. Same magnitude of velocity and same direction of velocity result same velocity. Simple name. Particle B and F have same velocity direction, and particle B and F have same magnitude of velocity, and therefore velocity of particle B and particle F are same. If you have any doubt, ask. That question is a nice question. It's a really nice question. Can learn lots of things. You can always link simple harmonic motion theories in transverse wave oscillation. Not only transverse wave oscillation, even the longitudinal wave oscillation also you can involve simple harmonic motion theories. Remember, whenever transverse wave or longitudinal wave propagates in a medium, all the medium particles are vibrate in a simple harmonic motion. That story is very important to think. 21, 20, 19, 18, 17, 16 story. 16. The motion of an insect. The motion of an insect living on a sand generates transverse wave traveling at a 50 ms minus 1 and longitudinal wave traveling at a 150 ms minus 1 along the sand surface. A scorpion can estimate the location of the insect from the difference delta t in the arrival time of these waves. If delta t is 4 into 10 to the power minus 3 seconds, the distance from the scorpion to the insect is not it's not a basically just basic question. This is anyone can do this question, not difficult, very basic question. Question number 16, 2009 level question, 2009 A level question number 16. Not a difficult question, anyone can try. 2009 A level question. Really basic question. Question number what? 16. 16. 16. 16. Now, what shall we do? Our ground and soil is the ground. Now that insect produce two waves. Let's say insect is at location A, right? Now when t equals 0, very carefully listen, when t equals 0, when t equals 0, insect produces two waves. One is transverse wave propagating with the velocity of 50 ms minus 1. Other one is longitudinal wave propagating with the velocity of 150 ms minus 1. This insect at point capital A generates two waves. One is transverse wave with a velocity 50 ms minus 1. Other one is longitudinal wave with a velocity 150 ms minus 1. This story. Where are the scorpion? Scorpion is at point capital B. Scorpion is at point capital B. Not difficult. Scorpion is at point capital B. I want to find the distance between scorpion and insect. I want to find this gap simple x. I want to find the gap simple x. That's my target. That's my target. I want to find the gap simple x. That's my target. That's my target. I want to find simple x. That's my target. Now when t equals 0 only, insect produce transverse wave as well as longitudinal waves. But based on their velocity difference, who has the larger velocity? Longitudinal wave has the larger velocity. So who will reach point capital B first? Is it longitudinal wave or transverse wave? Since longitudinal wave has the larger velocity, longitudinal wave will propagate the simplest distance and reach the scorpion at first. Okay? At first, if I draw the longitudinal wave in blue color, the time taken by longitudinal wave is, let's say, t1. Longi. Right? The time taken by longitudinal wave to move from A to B is how much? t1. What is the speed of longitudinal wave? 150 ms minus 1. Speed is 150 ms minus 1. V1 is how much? That is 150. Speed of the longitudinal wave is how much? 150 ms minus 1. 150 ms minus 1. Right? Okay. Right. The next one is transverse wave. Since transverse wave has the smaller velocity, they reach towards scorpion at point capital B after some time later. Right? Since longitudinal wave has the larger speed, longitudinal wave will reach the point capital B first, then only after some time later only, transverse wave will reach the point capital B. That means there is a delay reaching longitudinal wave and transverse wave. There's a gap. That gap is given. I draw the transverse wave in red color. Let's say time taken by the transverse wave is simple t2. Simple t2. What is the speed of the transverse wave? That is v2, 50 ms minus 1. v2 is 50. The delay of reaching the transverse wave to the scorpion, point capital B, the delay is given, delta t. That delay is given how much? That is how much? That is 4 into 10 to the power minus 3 seconds. Then tell me now tell me, out of this longitudinal wave and transverse wave, who will take more time? Since speed is lesser in transverse waves, transverse wave will take larger time. Since speed of the transverse wave is smaller, transverse waves will take larger time to reach point capital B. Therefore, T2 is larger than T1. T2 is larger than T1. Then delta T means, remember, T2 minus T1. That is your delta T. That logic, remember. T2 minus T1 is going to be delta T. That story very clear. The one having larger speed will take smaller time to reach simple x distance. One having smaller speed will take larger time to travel simple x distance. This is one story. For the longitudinal wave, you can apply S equals to equation. Right? Equation 1. Apply S equals to equation for longitudinal wave. Okay, S equals to equation. Right, S equals ut. But when you are doing this question, you should not use this equation. You should not write this equation in your steps. Longitudinal wave. Okay. Displacement is simple x. Distance between point A and point B. Distance between insect and the scorpion is simple x. What is the velocity of the longitudinal wave? That is, we know, 150. Time taken is simple t1. Simple t1. So you can write down simple t1 in terms of simple x. Simple t1 in terms of simple x, xo 150. xo 150. Likewise, if you find simple t2 also, if you apply S equals to equation for the transverse wave, speed traveled by transverse wave from A to B is simple x. Speed is 50. Time taken by transverse wave is how much? Simple t2. And then simple t2 going to be how much? X over 50. X over 150 t1, x over 50 t2. Substitute here. You want to find the simple x thing? You can easily find simple x now. This is why equation 1, equation 2, and then equation 3. Simplify it. But when you are doing this step, right, with your mind, try to somehow improve it. With your mind, you should understand, you don't want to do the diagram. You want to understand the one having larger speed will take lesser time to reach point capital B. The one having smaller speed will take more time, but both the waves will travel same distance. Therefore, you want to apply S equals to equation. Right, then you should not write this step also. Right, you should not write these two steps when you are doing MCQ, but you can write these two. You can write this one and you can write these three steps. Then directly substituting x over 150, x over 50 minus x over 150 equals LT. Then substitution. Likewise, reduce the steps as much as possible. Reduce your steps as much as possible. That is really important. Time is 8:25. Almost finished. Almost finished. Okay. Right. Then T2 minus T1. T2 is what? T2 is going to be x over 50. So x over 50 minus T1 is x over 150 must be equal to delta T is how much? 4 into 10 to the power minus 3. 4 into 10 to the power minus 3. 4 into 10 to the power minus 3. Okay. Now you can multiply up and down by 3. Right. Then here it's going to be 3x minus 2 minus x means 2x. If you multiply up and down by 3, here 3x minus x means 2x. 2x over 150. Right? 2x over 150 means x over 75. Likewise, you should be able to simplify it. 2x over 150 means x over 75. X over 75, it will go to this side, 75 into 4. Likewise, right? X over 75 must be equal to 4 into 10 to the power minus 3. When you substitute simple x going to be equal to how much? That is going to be equal to 75 into 4, how much? 300. 300 into 10 to the power minus 3 is how much? 0.3. 0.3 meter. 0.3 meter. Nice story. Nice story. Nice question. Answer is fourth one. 16 answer is fourth one. Then question number 16 done, 15 done, 14. 14 story done. 14 no, right? 14 no, I think. 14 idea. A student vibrates a tuning fork and listen to its sound while keeping it in air. A student vibrated a tuning fork and listened to its sound while keeping it in air. Then he vibrated this tuning fork again with the same amplitude and listened to the sound while placing to handle against a larger wooden boat. Larger wooden boat. The sound intensity heard by him in both the cases is same. The sound intensity heard when tuning fork goes on vibrating is higher than when it is held against the wooden boat. The time during which the tuning fork goes on vibrating is the same in both the cases. The time during which the tuning fork goes on vibrating is higher when it kept on the boat is more than air. The time duration which is tuning fork goes on vibrating is higher when it is kept in air than the boat. I think what the idea they are saying, the student vibrated a tuning fork, listen its sound while keeping it in air. Then he vibrated this tuning fork again with same amplitude and listened to the sound while placing to handle against a larger wooden boat. Then what will happen is, what the difference is, when you place it in the air and when you keep it on the wooden boat, when you keep it on the wooden boat, you will what? Sound intensity heard when the tuning fork goes on vibrating is higher than when it is held against the wooden boat. Sound intensity heard when the tuning fork goes on vibrating. Can someone share this Pesuru MCQ, this one's? Question number 6, 14th. Pesuru MCQ, someone can reply, someone can send? Can someone send a story? While someone sending 14 story, we'll go to 13. 13, 12. 13, 12. Then what pending? 13, 12. Question number 13, 12. And then only pending is 7. 13, 12, 7. 13. 13. An oscilloscope is connected to a microphone. An oscilloscope is connected to a microphone which received simultaneously a 50 Hz signal and another signal of frequency greater than 50. Okay. The figure A shows the trace with 50 Hz signal along, while the figure B shows the trace due to the combined signal. Okay, combined signal. Okay, right. The value of simple f is. Now this story they are talking about beat frequency story. Right? Okay. Look here. Look here. This idea. Nice question. If I do this diagram, look here. Right. 2006 level question. 2006 level question. This idea. What is the year? Question number 13 is the question number 13. Question number 13. Question number 13. Okay. I draw that diagram. I only draw this section. How many complete cycles we can see? How many complete cycles we can see here? Right here we can see. Okay. Right, we can see some like this. Listen very carefully. This idea. Listen very carefully. 1, 2, 3, 4, 5. Okay. This idea carefully. 1, 2, 3, 4, 5. Okay. Okay. This story. Okay. Right. Look here. Then this story. Something like this. Right. Now this question is really important question. Really nice question. Stay focused and learn something. Time is almost 8:30. Right. We started the session at 6:45, 7:45, almost 8:40. It's going to be 2 hours. It's going to be around 2 hours. Stay focused. Learn something. Right. Okay. Now basically this story is about beat frequency. We all learned that when there are two sounds having similar frequencies vibrating together, then we can see a kind of fluctuation in intensity, right? Then we called about beat frequency story. Okay. Now they mentioned oscilloscope is connected to a microphone which receives simultaneously a 50 hertz signal. The frequency of one of the waves is 50 hertz, right? So when you consider only the first sound is having a frequency 50 hertz. And a signal of frequency we don't know. There are two sound sources. There are two sounds. One sound is having a frequency 50 hertz. Other sound is having a frequency more than 50. We know it's very close to 50 only, more than 50, but we don't know exact frequency of the second sounds. We don't know the exact frequency of second sound. First sound has a frequency 50 hertz. Second sound also has a frequency greater than 50. We don't know exact value. That's what we want to find. Okay? Right. This shows the wave of sound 1. This shows the wave of sound wave of first sound. Sound wave of first sound. Right? Then let's say now all are sound waves, right? All are sound waves, they all are propagating in the air, thing like that. All are sound waves, they propagate in the air, thing like that. Then speed of all sounds must be same. Speed of all sounds must same. Okay. Now see. Now look very carefully. Now we can see what is the wavelength in this scenario. You can see that the same form is repeating again and again. This form is repeating again and again, right? This form is repeating again and again. 1, 2, 3, 4, 5. That means you want to understand. You should understand that means this gap is equal to one wavelength. You want to understand, right? This waveform is repeating again and again continuously. Clearly, this shape of the waveform is repeating again and again continuously. Then we can tell this as the wavelength of this sound. Frequency 50. Let's say speed of the sound is V. Speed of this sound is V. Wavelength is this lambda. Then tell me in terms of lambda 1. Lambda 1. Then what is the second diagram? Second diagram shows about the combined resultant wave fluctuation. So we are going to vibrate both sounds together, sound 1 and sound 2 together. Sound 1 frequency 50 Hz, right? Sound 1 wavelength lambda 1. Sound 2 frequency simple. If I don't know, I want to find sound 2 frequency only. When you vibrate sound 1, sound 2 together, the resultant sound wave is given in this below diagram. In the resultant wave diagram, this is repeating again and again, this shape. This shape is repeating again and again, right? This shape repeating again and again. Then we can tell this has the resultant, this gap as the wavelength of resultant sound wave. We can consider this gap as wavelength of resultant sound wave. This gap. Then what is the wavelength resultant wave? We all know that wavelength of resultant wave must be how much? Lambda 1. There are 5 lambda 1. 5 lambda 1. 5 lambda 1. Okay. Right. See very carefully what I am doing. So we know that sound 1, sound 2. Sound 2 has the larger frequencies F. Then we can tell beat frequency means what? Beat frequency means F1 minus F2. F1 minus F2. Then sound 2 has the larger frequency F ni. F, I want to find F only minus 50. 50 Hz belongs to sound 1. F belongs to sound 2. Beat frequency, let's take it as FB. So we all know that V equals F lambda equation. All sound waves are propagating in the air, thing like that same medium. Therefore, all the sound 1, sound 2, even the resultant sound is also have same speed V. Then we know V equals F lambda equation. We can remember V equals F lambda equation. According to V equals F lambda equation, subject F, then frequency means what? A velocity of the wave over wavelength. Beat frequency means, remember, the resultant wave of sound 1 and sound 2 frequency. Beat frequency means what? Resultant sound of sound 1 and sound 2 frequency. Then we can write it as V over lambda. V over lambda is how much? V over lambda is how much? V over lambda is how much? Lambda going to be how much? 5 lambda 1. 5 lambda 1. 5 lambda 1. Right? F means what? Sound 2 frequency V over lambda 2. Wavelength I don't lambda 2. Minus. Right? Minus. Okay? Minus. Okay, we can do this way only. We can do this way. Okay. Look here, we can do in this way. Since we know the F2 sound 1 frequency, since we know sound 1 frequency, we can find okay, look here, simple. We can do easily. When I consider sound 1, if you apply V equals F lambda equation, if you apply V equals F lambda equation for sound 1, if you apply V equals F lambda equation for sound 1, speed of the sound, just put it as V. Frequency of sound 1 is 50, wavelength is lambda 1. Lambda 1. Apply this V equals F lambda equation for the resultant sound wave of sound 1 and sound 2. Apply V equals F lambda for resultant sound wave of sound 1 and sound 2. Resultant sound wave. Then speed is V. Beat frequency, that is beat frequency FB. The wavelength lambda going to be 5 lambda. 5 lambda. When you equal, you will get what? You will get FB as what? If you equal them, V equals something, V equals something. 50 lambda 1 equals FB into 5 lambda 1. Then you are getting FB as how much? FB is going to be how much? FB is how much? Exactly 10 hertz. Beat frequency is how much? 10 hertz. Beat frequency 10 hertz. Then we know beat frequency means we all know that sound having larger frequency f minus 50. 10 f minus 50 is how much? What is your f? 60 hertz. Nice question, okay? Nice question, 60 hertz. 60 hertz, nice question. Real nice question. Time is 8:40. Time is 8:40. Real nice question. Real nice question. Question number 13 also done. Third one discussed. Nice question. I think if you have any doubts, you can ask. If you have any doubts, you can ask. This is the best way. Very simple story. Now, very simple. Now, they have given two sound waves. Sound wave 1, sound wave 2. They gave the frequency of sound wave 1, that is 50 hertz. But sound wave 2 frequency they haven't given, but they mentioned sound wave 2 has a frequency greater than 50. When you vibrate sound wave 1 and sound wave together, the resultant wave is shown in this diagram. Identifying this length as the wavelength of resultant wave. Identifying this wavelength is 5 times greater than the wavelength of sound wave 1. Then identifying this one's frequency is the beat frequency. Beat frequency. Those stories are really important stories. Nice question. Put a star. Put a star. Nice question. Put a star. Nice question. Nice question. Nice question. No time. Time is flying. Time is flying. Time is flying. No question. Time is flying. Time is flying. Time is flying. Okay. Time is flying. Right? Story. Story, okay. Next story, next story, next story, next story. What is next one? Next idea is what? Next idea is what? Next story. Now learn, okay? Learn, okay? Done. Question number 13 also done. 14 one discuss, okay? I'll come to 14. Then next one is 12th one. Earthquake which occurs at a certain location generates a transverse wave, S wave, secondary wave, and a longitudinal wave or capital P wave. Both waves travel through the Earth and capital P wave arrives 3 minutes before the S wave. Capital P wave arrives 3 minutes before the S wave at a certain point on the Earth. The average speed of S and P waves between the points and the location of the earthquake are 4 km per second and 8 km per second respectively. How far away from the point did the earthquake? Okay, same story, same question. They are asking simple X. Again, they are asking simple X, same story. Now, earthquake occurs at point capital A. This is a point on the ground. There are two waves, primary and secondary. Primary waves are longitudinal wave. Secondary waves are transverse waves. Okay. Primary waves are longitudinal wave. Secondary waves are transverse waves. Right. They are asking again the distance simple X only. They are asking same question. Same question they are asking. 2006 question. Same question. Same story. Same story. Same story. 2006 question. 2006 A-level question. Idea. Right? Question number 12. 12th idea. Same idea, okay? Same story. Okay? Longitudinal wave. What is the velocity? We know out of primary and secondary, primary waves are longitudinal. Secondary waves are transverse. Am I correct? Okay, transverse wave secondary, longitudinal wave primary. They have given the speeds. They have mentioned that the average speeds of secondary and primary waves between the point and the location of the earthquake are 4 and 8. Right? Longitudinal wave speed is how much? 8 km per hour. 8 km per hour. And what is your V2? Speed of the transverse wave, if not secondary wave, is how much? that is 4 kilometer per hour. 4. V2 is 4. The time, that delay, delta is how much? Delta is given as 3 minutes. Delta is given as 3 minutes. Okay, can do, can do, can do, can do. Same story. Then here you want to understand here now. T1 means what? X over 8. I don't do from the beginning. I think you understood how I obtained these equations. If you apply for longitudinal wave, if not, that is your primary wave. Primary wave, if you apply the equation S equals ut, right? S equals ut, what is the time taken by the longitudinal wave to reach the ground is t1. T1 is going to be x over distance between earth quark point and the point on the ground, that is simple x. I want to find simple x only, right? Simple x only I want to find. Then speed of the longitudinal wave is how much? 8 kilometer per second. 8 kilometer per second is 8. Likewise, if I apply the equation S equals ut for the transverse wave, that is the secondary wave, that is simple T2. T2 going to be how much? That is going to be x over 4. Speed of the transverse wave, secondary wave is 4. 4, it's 4. Then which one is larger? X over 8 is larger, x over 4 is larger. X over 4 is larger, x over 8 is smaller. Therefore, remember x over 4 minus x over 8. The difference equals how much? 3 minutes. X over 4 minus x over 8. The difference of the time, difference between T1 and T2 must be equal to 3 minute delay. 3 minute. If you convert 3 minutes into seconds, 3 into 60. Then you can find the x easily. Then you can find the x easily. If you can convert 3 minutes into seconds, you can find the answer easily. You can find the answer easily. Right? So I multiply up and down by this x over 2. If I multiply the numerator and denominator by 2, 2 and 2. Then here 2x minus x, that is how much? 2x minus x, how much? X, x over 8. X over 8 going to be how much? X over 8, that is equal to 3 into 60, 180. Okay, 180. If you substitute simple x is how much? Simple x is going to be how much? Simple x is going to be 180 into 8. That is equal to 0, 8 into 8 is 64, 1440 kilometer. 1440 kilometers. Nice question. Nice question. This question is exactly same as question number 16. Same story, same idea. Only the speed and the delay of time is different. That is the only difference. That question also discussed. Time is almost 8:50. Right, the last story. The last few stories. The last few stories. Okay. The last few stories. We'll do the pending questions in our entire tutor and we'll finish the tutor and we'll start the optics past paper questions. Time is 8:50. We'll take a break. We'll take a break and come soon. Time is 8:50. We'll take a break. Time is 8:50. Come at 19. Take your break. Come at 19. So we are doing the class till 11 o'clock. Come at 19, 11, 11:15 sometimes. Come at 19. Right, okay. Right. Okay, then we'll continue the remaining story, remaining few more questions. And the last two questions. I think last two questions. Last two questions. Look here. Last two questions. Page number. We were talking about properties of waves, right? Question number 14. Answer is fourth one. Okay. Please just read the question and put the idea in your short note point book also. Question number 14. Answer is fourth one. Okay. Then next question is 2000. The last question, pending question is question number 7. 2002 A level, question number 7. 2002 A level, question number 7. The last story. 2002 A level, question number 7. Now stay focused, fully bright. If you focus and if you cover this entire part of the story, then you can relax that. You can relax. Okay, I have done even the past papers from this relevant sections also. I completed. They must stay focused, right? 2007 level question finished. This idea. The last question, seventh one idea. They have given a wave propagating to the right side and they have given a point capital P. That wave is propagating, the wave front is propagating right side and there's a point capital P. Clear? It's clear. It's point capital P. A pulse propagates with a uniform speed along a straight string as shown in the figure. Which of the following best represents the displacement of the point of the string with time? Now just think what will happen for the point capital P. This pulse propagates right side direction. Then what would happen for the pulse? Sorry, what would happen for the point capital P? Right? If you draw the displacement time graph, look here. Now we know this point capital P will move in a simple harmonic motion. Okay? Capital P will move in a simple harmonic motion. They are asking us to draw the displacement of the point. Look here. Simple D versus time. Right, till the wave pulse reaches point capital P remains stationary at same location. Displacement of the pulses remains stationary. Displacement is, we can take it as 0 also, right, remains stationary, but based on the given graphs, they haven't mentioned in the beginning displacement is 0. Therefore, displacement is same, okay. As the pulse reaches point capital P, what will happen? This point capital P will move upwards. Then again, this point capital P will move downwards, right? When this wave pulse propagates through point capital P, your point capital P will move upwards. And then point capital P will move downwards. That's what's going to happen. Displacement will increase and decrease. Simple story. Therefore, the right answer going to be answer is second one. Second one, that section completely discussed. I think we have some pending MCQs in longitudinal waves. We are going to that story also. Right, we are going to that story also. Someone remind me simple harmonic motion recordings. If you want me to upload simple harmonic motion recordings in a February course, January close, someone remind me. Right? If you want me to upload simple harmonic motion recordings in February or January course, please someone remind me, okay? Then that chapter fully done and dusted. All clear, put a small YouTube reply. All clear, all nice, all super, put a reply. All clear, all nice, all super, put a reply. All nice. Great, nice, put a reply. Put a reply. All clear, all nice, put a reply. Reply everyone, all good. Reply everyone, all good. Give me a small reply. Give me a small reply, all good, all nice. Reply. So reply. Nicely, nice story. I think almost done now. We won't talk about Doppler effect. Past paper MCQs are not included in this paper book. So we want to talk about Doppler effect questions as well as optics questions. That story. All nicely, all beautiful. Pending questions. I think Amaya sent right pending questions. Longitudinal waves, electromagnetic waves we completely finished. Intensity completely finished. Transverse waves also completely finished. Longitudinal waves we have some questions. I think we didn't do question number 7, 8, 11, 13, 18. We'll do now. We'll do now. Then story finished. Then story finished. This book will be finished in. Right? Okay. Right, give me 1 second. Next story. Give me 1 second. Next story. Right? Next idea. Okay. Right. Okay. The pending questions. Go to the longitudinal wave section. Okay. Right. Question number 7. Page number longitudinal wave question. Page number 20. Question number 7, 8. Right. The last few stories finished. Again, continuation of longitudinal waves. Past paper MCQs. Longitudinal waves. Longitudinal waves. Okay. Then 1990 T level question number 7. Okay. 1998 A level question number 7 I could not do because there was a mistake in the question. Therefore, refer the page through PDF also. Question number 7. If you refer the page through PDF, page through PDF. Page through PDF. Okay. Okay. All right. Okay. Right. It is mentioned that to the fundamental frequency produced by a certain closed and opened RC. The fundamental frequency produced by a certain closed and open end tubes are same, I think. There is a one end closed tube and both end open tube. Both of them are producing same fundamental frequency. That's what I think. Okay. The open pipe is inserted fully into the closed pipe until it hits the bottom of the closed pipe. If the end connections are neglected, the corresponding fundamental frequency of the new setup will be. Right. Okay, listen. This idea. Right? They mentioned the open pipe is inserted fully into the closed pipe until it hits the bottom of the closed pipe. If the incorrections are neglected, then the corresponding fundamental frequency of the new setup will be okay. Right, this story. Okay. Now there are two tubes. One is one in closed tube, other one is both in open tube. Okay, one in closed tube, other one is both in open tube. As per my understanding, the length of the open end tube must be greater. We'll see. Other one is both an open tube. Okay, right. Then length of one enclosed tube is simple L1. Length of both end open tube is simple L2. simple L2. This one going to be simple L1. Simple L1 length, right? Simple. But they clearly mentioned that the air column inside both the tubes vibrate under fundamental frequencies and they are equal. The fundamental frequency of one and closed tube as well as fundamental frequency of both and open tube are same. If not, right? So we know one and closed tube fundamental frequency equation is VO4L. For one and closed tube, fundamental frequency equation is VO4L. Right? VO4L, length of the closed end tube is L1. Therefore, I put L1. This equation is applied for one and closed tube. If you apply the equation for both and open tube, fundamental frequency equation for both and open tube is what? V over 2L. Right? F naught is equal to what? V over 2L. F naught equals V over 2. Length of the open end pipe is how much? L2. L2. And then you know that you want to understand VO4L1 must be equal to VO2L2. Clear? F naught, same fundamental frequency. Therefore, you can equal the equation 1. This is going to be equation 2. You can equal equation 1 and 2. In that case, you will get the answer. You will get the answer that. You will get the answer. VO4L1 must be equal to VO2L2. Simply. V over 4L1 must be equal to V over 2L2. Right, to this V, this 2 cancel out, here it's going to be 2D. Finally, you can obtain a relationship between L1 L2. Simply L2 is how much? Length of the both end open tube is twice the length of one end closed tube. This story, right? Right. That means both end open tube has a length equal to twice the length of one end closed tube. L2 going to be equal to 2L1. L2 going to be equal to 2L1. Right. Okay. Then what they are saying, they are going to insert this both end open tube completely inside one end closed tube. Now story. Now what they are telling? Right? This both end open tube going to completely insert in the one end closed tube. What will be the result? The result is again one end closed tube. If you insert both end open tube completely inside one end closed tube, the result is what? Again, we will obtain a one end closed tube. Right? So before there was L1, this closed end tube has a length L1, fundamental frequency is F naught. Now what is the length of this newly formed one end closed tube? L2. If not, that is 2L1. If you insert this L2 both end open tube completely inside this one end closed tube, the result is again one end closed tube having a length L2, having a length 2L1. That's it. This is having a length 2L1. So what is the fundamental frequency equation? Let's say fundamental frequency of this one end closed tube is F naught dash, that must be equal to V over 4, length is V over 4L, length is 2L1. 2L1, equation number 3. So what you can do now? If you divide F naught equals V over 4L1, if you divide equation 3 by 1, if you divide equation 3 by 1, you get the answer. Divide equation 3 by 1, you will get the answer. So we are getting the answer F naught dash. That is going to be equal to how much? F naught dash over F naught. This must be equal to what? If you simplify properly, then this V, this 4, this L1 cancel out. Okay, you do the simplification properly. I don't do the simplification. Right, V over 4L1 cancel out with this V over 4L1. The remaining is half. I feel like F naught is F naught over 2. F naught dash is equal to F naught over 2. You guys do simplification. That is the answer. F naught over 2. Question number 7 answer must be F naught over 2. Any doubt you can ask. That story. A basic simplification, divide equation 3 by 1. Then you can obtain if not dash in terms of if not. Very simple idea, not difficult. Then eighth one story. Question number 8. Eighth one idea, when two organ pipes of length. The problem is normally they should tell properly whether this, now for this question it's not relevant. For this question to get the answer, this story is not relevant. I think we can get the answer without considering whether it's an open-end tube or closed-end tube. But the fact is, they should mention whether that organ tube is both-end open tube. If not one-end closed tube, they should mention. If not, it's a real trouble, right? Some questions, they take organ tubes as what? Both-end open tube. Some scenarios, they consider organ tubes as one-end closed tube. Mostly organ tubes means both-end open tube, right? They should mention properly. Question number 8, 19 and 11 question. 19 and 11 question. A-level question. Question number 8. Question number 8 story. 8 story. When two organ pipes of length 50 centimeter and 50.5 centimeter are sounded together, 3 beats per second per hertz. 3 beats per second are heard. If the incorrection are neglected, the frequencies of the pipe are respectively. When two organ pipes of length 50 centimeter and 50.5 centimeter are sounded together, 3 beats per second are heard. Now let's consider now. It doesn't matter. See the logic. It doesn't matter now whether both pipes are open-ended pipes. If not one-end closed pipes, we all know that if those pipes are one-end closed pipes, if those two pipes are one-end closed pipes, what is the equation to find the fundamental frequency? Fundamental frequency F naught equals V over 4L. If both the pipes are open-end pipes, both-end open pipes, what is the fundamental frequency equation? F naught equals V over 2L. Anyhow, both scenarios we all know that fundamental both are either open or both are either closed. Therefore, fundamental frequency is directly proportional to 1 over the length of the tube. That logic, you can directly use that logic. You can say that fundamental frequency directly proportional to 1 over the length. Then, let's say then one tube has a length 50 centimeter, other one's length 50.5 centimeter. Then let's say fundamental frequency of first tube is, the fundamental frequency of first tube is F naught something, F naught proportional to 1 over 50 centimeter. Then F naught dash proportional to what? 1 over 50.5 centimeter. If we divide proportionally 1 by 2, what is the answer? Divide proportionally 1 by 2. What is your answer? If we divide 1 by 2, the answer is going to be how much? Answer is going to be F naught over F naught dash. Simply, F naught over F naught dash. F naught over F naught dash, that must be equal to 50.5. 50.5 over 50. 50.5 over 50. Then you can write down now. F naught means what? F naught means 50.5 over 50. If not 5.05, 1.01. F naught equals how much? 1.01 F naught dash. Then beat frequency means what? Beat frequency means F naught minus F naught dash. We know beat frequency, beat frequency means what? F naught minus F naught dash. Why? Because F naught is greater than F naught dash. That's why F naught is greater than F naught dash. Therefore, beat frequency they have given, that is 3. What is my F naught value? F naught value, what they are asking? They are asking F naught and F naught dash. They are asking F naught means what? 1.01 F naught dash minus F naught dash. Now you can easily find the F naught dash value. Then 3 equals, if you take F naught dash as your common factor out, 1.01 minus 1. Finally, F naught dash going to be how much? 300 hertz. You simplify it. 1.01 minus 1 is 0.01. F naught dash means 3 over 0.01 is 300. 300 hertz. You can simplify it and get the answer 300. If your F naught dash is 300, what is your F naught? F naught dash 300 means, right, from equation 3 something. F naught dash 300 means, what is your F naught? 303. Your F naught going to be how much? 303 hertz. Can do. Can do. That question answer, we can find the answer in 303 and 300. Simple question, nice. 7, 8 done. What is pending questions? 7, 8 done. We have 5 pending, 2 done, remaining 3 pending. What are the pending questions? They are then next story is question number, I think 11. I think 11 pending. Question number 11 pending, I think. 11 pending. 11, 13 pending. 11, 13, 18, I think. 11, 13, 18 pending. Then finished. Entire book finished. 11, 13, 18. Then entire book finished. 11 idea. 11 idea. Organ pipe filled with oxygen has a fundamental frequency F naught. Organ pipe filled with oxygen has a fundamental frequency F naught. If the pipe is filled with hydrogen at the same temperature and pressure, the new fundamental frequency of the pipe is. This is the idea. Again, they haven't mentioned, I think they should mention whether the pipe is one enclosed pipe or both an open pipe. They should have given. They should mention the organ pipe is one enclosed pipe or both an open pipe. They should have given. But they haven't given, but you can get the answer. Even though they haven't given whether it's one enclosed pipe or both an open pipe, we can get the answer. Right? We can get the answer. We all know the story. Look here. So we all learned if you can remember velocity of sound in a gas. What is the equation? V equals gamma RT over capital M whole root. Clearly mentioned in the question, temperature constant. But when you are using different gases, since velocity of sound in a gas depends on the molar mass, when they are using different gases, obviously, velocity of the sound in the relevant gas going to be different. Going to be different. Okay, right. 2007 question, the last few stories. 2007 A level, the last few stories. Okay. Right. Okay. Listen, right, okay, idea. Question number 11. 11, we all know this equation. Velocity of sound in the gas. That is equal to what? Gamma RT over capital M whole root. Gamma RT over capital M entire root. Entire root. Gamma RT over capital M entire root. Since they mentioned temperature remains constant, capital T, capital R, gamma constant. But they are talking about oxygen as well as hydrogen. Therefore, we know that velocity of sound is proportional to 1 over root capital M. We all know that. Then, if the gamma RT same for hydrogen as well as oxygen, right? Velocity of sound is proportional to 1 over root capital M. 1 over root capital M is logic. Okay. Then let's say velocity of sound in first they tell what? First they say what? Velocity of sound in oxygen too. Okay, what they're telling first? Organ pipe filled with oxygen has a fundamental frequency F naught. Pipe is filled with hydrogen. Same temperature, pressure, new fundamental frequency of the pipe. Okay. Let's say velocity of sound in oxygen is V naught over, if you use this proportionality, okay, I will follow everything. We can easily write down V naught to VH equals MH to M naught whole root. Right? If okay, velocity of sound in oxygen is proportional to 1 over molar mass of oxygen. Proportional to 1 over root molar mass of oxygen. Proportionally 1. But don't do like that. What you do, don't write this equation. Don't write this equation also when you're doing the MCQ. Only write down velocity of the oxygen is proportional to 1 over root molar mass. Not even this one. You should write down only this one. V naught to VH, velocity of sound in oxygen over velocity of sound in hydrogen, is equal to molar mass of hydrogen over molar mass of oxygen root. First, if you can directly write down this, it's really better, right? It's not difficult, right? You know that, you know the story, temperature. You can, in your mind, you can think these things. Temperature remains same, R same, gamma same. Then velocity of sound only proportional to 1 over root capital M. Then V oxygen to V hydrogen must be equal to capital M hydrogen over capital M oxygen entire root. That story you can think in your mind. But I'm following everything properly. Therefore, if you apply this proportionally for hydrogen gas, if I apply this proportionally for the hydrogen gas, what? Velocity of hydrogen, that is proportional to, have they given the molar masses? They have given the molar mass of hydrogen and oxygen. They have to directly write down velocity of oxygen is proportional to 1 over molar mass of oxygen. That is 16. Molar mass of oxygen is 32. Velocity of the hydrogen, velocity of the sound in hydrogen gas. Velocity of sound in oxygen gas. Velocity of sound in hydrogen gas proportional to 1 over molar mass of hydrogen is how much? That is 2. So you can easily write down, proportionality, if you divide proportion 2 by 1. Proportion 2 by 1, you can write down what? You can write down easily VH to VO. Velocity of sound in hydrogen gas over velocity of sound in oxygen. This is equal to what? Equal to root 32 over root 2. 32 over 2 is how much? 16. Root 16 is how much? 4. VH is equal to how much? 4 VO. This story. Right? Now, when I am following some steps for everyone to understand, but directly you can write down this equation. Directly, anyone can write down this equation. Okay? Velocity of hydrogen or velocity of oxygen is equal to how much? Root 32 over root 2. 32 over 2 is how much? 16. Entire root 16 is how much? Just 4 V naught. This is, I take it as equation 3. Equation 3. They are saying what? They are saying an organ pipe filled with oxygen, fundamental frequency. Now same pipe. The same pipe, same, I don't know, they mentioned organ. Maybe it can be one enclosed pipe. Maybe it can be both an open pipe. I don't know what is the pipe type exactly. But that pipe, either closed end or both an opened end, its length remains same. Only what we are doing, earlier pipe was filled with oxygen, now pipe is filled with hydrogen. So therefore length of the pipe and all is same. Then we know fundamental frequency only proportional to what velocity? Look here. In case if it is one enclosed pipe, what is the fundamental frequency equation? If it is one enclosed pipe, what is the fundamental frequency equation? F naught equals V over 4L. In case if it is both an open tube, what is the fundamental frequency equation? F naught equals V over 2L. So basically you want to understand fundamental frequency now. Length means both the scenarios. When you fill in the same tube, when you fill oxygen now, the same tube, when you fill hydrogen, fundamental frequency is only proportional to the velocity. Same length. Therefore, you can just write down, fundamental frequency is proportional to velocity only. Velocity is proportional to what? 1 over molar mass. 1 over molar mass. So you can write down fundamental frequency in the oxygen proportional to velocity of sound in oxygen. Fundamental frequency in hydrogen is proportional to velocity of sound in hydrogen. If you divide them, there are different ways. If you divide them, what you are getting? F naught to FH must be equal to what? V naught to VH. V naught to VH. What is the answer? V naught to VH. What is the answer? They are asking FH. They are asking FH. V0 to VH. VH to V0, it's 4. V0 to VH, 104. This is 104. 104. F0 over FH is how much? 1 over 4. When you substitute frequency of hydrogen, that is going to be 4 simple F0. 4 F0. Answer is fifth one. Question number 11. Answer is fifth one. Very simple question. Now see this idea. This idea very simple. This idea, I think we can get the idea. Okay, I just did it along with it. Okay, small method. Okay, small method means small idea. Listen carefully. 9:45, 10:45, 11, 11:15. Listen very carefully. This idea very clearly. Fundamental frequency proportional to what? Velocity. How I opt this proportionality? We know that F0 is equal to V over 2LO, V over 4V. Therefore, same length. Therefore, fundamental frequency is directly proportional to the velocity. Velocity of the sound in a gas directly proportional to what? 1 over molar mass. 1 over molar mass. Then one can tell fundamental frequency proportional to 1 over molar mass. 1 over molar mass. Therefore, you can write down fundamental frequency in the oxygen over fundamental frequency in the hydrogen must be equal to molar mass of hydrogen over molar mass of oxygen. Hydrogen molar mass how much? 2. Oxygen how much? 32. Entire root 1 over 16 root means 1 over 4. Then FH is how much? FH equal to 4F0. Simple story. Simple story, nice question. Then that is also done. The last two MCQs. Entire book is finished. Last two MCQs. Figure shows a speaker mounted at B at a certain distance. Okay, last two stories. Stay focused. Last two stories. Last two ideas. Last two ideas. Last two idea. (2011) question. 2011 question. Figure shows a speaker mounted at B at a certain distance from a smooth wall A and emitting a sound of single frequency. When a sound detector which is sensitive to pressure variation is taken from A to B, a minimum of sound level is detected at 2 meters from speed scale. Well, speed of sound in air 320. Frequency of the sound emitted by the speaker is could be. We'll go to page story. We'll go to page idea. Question number 13. Question number 13, page idea. Question number 13, page idea. What is the page idea? Page idea 13. Right? Page idea. That question right. That question, okay. Now that question says in Pesuru PDF, figure shows a speaker mounted at B at a certain distance from a smooth wall capital E, and emitting a sound of single frequency. When a sound detector which is sensitive to pressure variation, is taken from A to B, A minimum of sound level is detected at 2 meters from the wall. Minimum of sound level is detected at 2 meters from the wall. Speed of sound in air is 320 ms minus 1. The frequency of the sound emitted by the speaker could be. The frequency of the sound emitted by the speaker could be. Right, the problem is what do they mean by minimum of sound level? Sound level minimum. Sound level minimum, okay. Decided, okay. Two, nice question. Put a star, nice question. Put a star, nice question. Now this is this behavior. Sometimes when you are trying the question, this idea, I think most of you didn't get this idea, I think. Right, by looking at this diagram, you should convert it into a one-end closed tube. But understanding this example is almost equivalent to a one-end closed tube air column vibration. Many don't understand. Many can't get that idea. This story is belongs to air column vibration in a one-end closed tube story. Many don't understand. If you can understand a story, I think most of you, even you don't understand also fair, suddenly, because this is a nice question. Look here, look here, look here, look here, right? So you want to assume this as one-end closed tube. Because there is a boundary, there is a rigid vertical wall, and this is this is horizontal ground, and here is your speaker, here is your speaker. Therefore, almost when the sound wave propagates through this air column, actually the sound is propagating through the air in the surrounding. So we can approximately think this sound wave is propagating through an air column trapped inside one-end closed tube. This region is almost equivalent to a one-end closed tube. One-end closed tube. Okay? One-end closed tube. Okay? Right. Now this is point capital B, point capital A, point capital B, point capital A. It is point capital B. This is point capital A. This is point capital B something. So what they mentioned is, when they are moving that detector from A to B, they realized exactly at 2 meters from A, right? They mentioned what? When a sound detector which is sensitive to pressure variation, because we know when sound wave propagates through air, through a gas, it produces compressions and rearfractions. We know sound wave is basically a longitudinal wave. When a longitudinal wave propagates through air or any gas, the medium particles, air or gas particles, compress, undergo rearfraction, compression. During the compression regions are having high pressure regions, rearfraction regions are having low pressure regions. They mentioned, remember, high pressure means intensity is high, low pressure means intensity is low. Do you understand? When the medium particles are well dispersed, well distributed, pressure is low, right? The low pressure means we all know that low intensity, okay? Right? Okay. Sound detector which is sensitive to pressure variation is taken for A to B, minimum sound level. That is minimum pressure. Minimum pressure. Minimum pressure is detected at 2 meters from the wall. Okay? If I draw exactly at 2 meters from the wall, sound detector detected a minimum pressure. Exactly at 2 meters from the wall, sound meter detected a minimum pressure. We know that pressure is minimum means what can you say about the displacement of the medium particles? Maximum. Exactly at 2 meters from the wall, detected pressure is minimum. Pressure minimum means what can you say about the medium particle vibration displacement maximum? Displacement maximum means we all know that exactly at 2 meters from the wall there must be a antinode, displacement antinode. If I draw this part, it's going to be like this. If I draw the wave pattern, standing wave pattern, it's going to be like this. Clear, right? Then we all know this is half a loop. Length of half loop is how much? Lambda over 4. Length of one loop is lambda over 2. Length of half loop is how much? Lambda over 4. Remember, hereafter put in a short run point book also. Length of half loop is how much? Lambda over 4. So lambda over 4 must be equal to how much? It's 2 meter. The wavelength of the sound wave propagating through this air column is how much? 8 meter. So when you apply V equals F lambda equation, velocity is given as how much? 320. Velocity of sound propagating through that air column is how much? 320 ms minus 1 equal to. They are asking us to find what frequency? The frequency of the sound emitted by the speaker. I want to find frequency, simple. If the wavelength I found 8 meter. Therefore, we are getting the frequency as how much? Frequency is 320 over 8 is how much? 40 hertz. The frequency must be 40 hertz. The frequency must be 40 hertz. 40 hertz. That story. The frequency must be 40 hertz. That story clearly. That story clear. That story clear. That story clear. Okay. Right. That story clear. That story clear. The last one pending. The last one is what? What is the last one? Last question. The last question is what? The last question. The last one must be. Question number 12 done, 13, 14, everything done. What is the last question pending in that tute? The last question. I think all discussed, right? The last one is what is the last one? We have done everything. The last one is what? The last one is. What is the last one? The last one. Right, 18, right? 18. I think 18. 18. When a tuning fork is sounded with a tube closed at one end, filled with air, at temperature 51 degrees Celsius, beat frequency of 4 Hz is heard. Same beat frequency is heard when the tuning fork is sounded with a tube filled with air at temperature 127 degrees Celsius. In both situations, the tube is sounded with same overtone. What is the frequency of tuning fork? What is the frequency of tuning fork? Neglect the incorrection of the tube. The last question. I think 18. 18 is our last question. Story finished. Anything pending? Tell me quickly. The last question is 18. Anything pending? Tell me quickly. The last question is 18. Anything pending? Tell me soon. Okay. All right. Okay. All right. Right. The last question. The last question. The last story. Okay. Just keep on trying. Just keep on trying to the last question. Just keep on trying the last question. The last question 18. 2022 variable question. 2022 variable question. 2022 variable question. 2022 A level question. Number 18. Number 18. The last story. The last story. Okay, right. Now there's a tuning fork and one end closed tube. Air column is inside, one end closed tube. Tuning fork is sounded with a tube closed at one end, filled with air at temperature 51 degrees Celsius. Beat frequency 4 Hz. One end closed tube air. See, look here. Let's say the frequency of the tuning fork is simple if. I want to find actually the frequency of this tuning fork only. I want to find simple if only. Simple if only. My target is find a simple if. When you vibrate this tuning fork together with air column inside the one enclosed tube, the beat frequency heard is how much? The beat frequency heard is how much? Right? Beat frequency of 4 Hertz is heard. 4 Hertz is heard. But at the moment, temperature of the air column is how much? Exactly 51 degrees Celsius. If you convert 51 degrees Celsius into Kelvin, how much? 273 plus 51. If you convert 51 degrees Celsius into Kelvins, 273 plus 51 is how much? It's 4, it's 12, 324. 4, it's 12, 324. Right? The air column. Just think this air column vibrates under fundamental frequency. Think like that. The air column vibrates under fundamental frequency. Same closed-in tube, same length. Same closed-in tube in same length. Same length. Temperature is what? Temperature is 51 degrees Celsius in Kelvins. How much? 324 Kelvins. Temperature. 324 Kelvins. Right? So then, beat frequencies, they have given how many beat frequency? Beat frequency is given as how much? That is 4 Hertz. So you can find the fundamental frequency of this air column. For one enclosed tube, what is the equation to find the fundamental frequency? V over 4L. Right? Fundamental frequency F naught, that is equal to what? V over 4L. Right? V over 4L. Look here. Fundamental frequency is equal to V over 4L, the equation. Look here. V over 4L. Basically, we are not changing the length of the closed-end tube. Right? Remember, the length of the closed-end tube remains same simply. Basically, what is changed? Temperature of the air column inside this one-end closed tube is changed. Temperature of the air column inside this one-end closed tube is changed. Therefore, we can tell that fundamental frequency proportional to the velocity. Velocity is proportional to what? V equals gamma RT over capital M whole root. Whole root ni. Now both scenarios, when you read the question, you realize both the scenarios are using air. Therefore, molar mass same for both scenarios. Gamma R same for both scenarios. But temperature is different. Therefore, we can tell velocity of sound in that air column is proportional to root absolute temperature. From this equation, fundamental frequency in a closed-end tube is V over 4L. You can say that fundamental frequency is proportional to V. From this proportionality 1, proportionality 2, what you can write down? From this proportionality, from this equation, one enclosed tube vibrates under fundamental frequency. Fundamental frequency proportional to velocity of the sound in that air. Velocity of sound in that air is proportional to what? Root absolute temperature. And then from proportionality 1 and 2 we can write down fundamental frequency proportional to what? From 1 and 2 we can write down fundamental frequency proportional to what? What? Root absolute temperature. That means large the temperature, large the fundamental frequency. In the beginning, temperature of the air column was 51 degrees Celsius. Later what they mentioned? Later they say what? Later they say same beat frequency is heard when the tuning fork is sounded with a tube filled with air at temperature 127 degrees Celsius. If you convert 127 degrees Celsius into Kelvins, how much? 273, 400 Kelvins. When you convert 127 degrees Celsius into Kelvins, how much? 273 plus 127. 273 plus 127 is how much? 400 Kelvins. 400 Kelvins. Right? The next scenario here. Here fundamental frequency is how much? This scenario, F naught is proportional to 51 degrees Celsius means 273 plus 51 is how much? 4? 324. 324 whole root. Proportionally simply. The next scenario, same tuning fork, but you are going to vibrate the tuning fork with one enclosed tube, but this time air column has a temperature 127 degrees Celsius. Now the air column has a temperature 127 degrees Celsius. In that case, the story. Now you have air column, now same tube length, but temperature 127 degrees Celsius, in Kelvins 400 Kelvin. Same tuning fork frequency FF. But now the fundamental frequency of the air column inside this one enclosed tube is, let's take it as F naught dash. Then from this proportion you can write down F naught dash proportional to what? Proportional to 400 root. Proportionally simple B. Then tell me which one is larger? F naught is larger or F naught dash must be larger. Root 400, large the temperature, large the fundamental frequency. F naught dash larger than F naught. They mention both scenarios. Look here. Tuning fork frequency is simple if I want to find the tuning fork frequency only. My target is I want to find tuning fork frequency only. Right? So we all know that F naught dash is greater than F naught. In the beginning, when you vibrate the tuning fork with this one enclosed tube at 324 kelvins, the beat frequency, the frequency of the one enclosed tube is how much? That is F naught. Your F naught must be somewhere here. The beat frequency is 4, this gap is 4 Hertz. After increase the temperature of the air column to 400 kelvins, now frequency of the air column is how much? F naught dash. The gap is also same as 4. 4. Now hereafter you can get the answer. Hereafter you can get the answer. Right? Hereafter you can get the answer. You can get the answer. Can get the my target is finding simple if. My target is finding simple if. What you can do now? You can divide proportional simple A by proportional simple B. If you can divide proportional simple B by proportional simple A. If you divide proportional simple B by proportional simple A, right? F naught dash over F naught. F naught dash over F naught must be equal to how much? 400 root over 324 root. 324 root. This story. Therefore, F naught dash must be equal to how much? 400 root over 324 root F naught. If you have doubts, you can ask in the chat. Keep on doing. Keep on doing. If you have doubts, you can ask via the chat. Keep on doing. Keep on doing. If you have doubts, you can ask via the chat. Keep on doing. Keep on doing. Keep on doing. Keep on writing the questions. Keep on trying the question. Don't waste your time. Keep on writing the questions. Right? Don't waste your time. Keep on doing the questions. Keep on doing the questions. Don't waste your time. Keep on doing. Keep on doing. Don't waste your time. Keep on doing. Keep on doing. Keep on doing. Keep on doing. Now can get the answer. Now you all can get the answer. You all can get the answer. I want to find simple if. I want to find simple if. One can find different ways are there. One can find F naught. Okay. Because we know the gap between F naught dash and F naught is how much? 8. The gap between F naught dash and F naught is how much? 8. Can get the answer. Get the answer. Get the answer. Now 400 root is how much? 20. F naught dash is how much? F naught dash root 400 is 20. They asked to consider 324 root as what? 18. 18. 18. 10 over 9. F naught. 20 over 18 is how much? 10 over 9. F naught dash means 10 over 9. F naught. Then we know F naught dash minus F naught, this gap, the difference between F naught dash and F naught is how much? Exactly 8. F naught dash minus F naught must be exactly equal to how much? 8. F naught dash how much? 10. F naught over 9 minus F naught must be equal to 8. Finally, F naught common factor. 10 over 9 minus 1 is equal to 8. 9, 9. Finally, you are getting the answer. F naught is how much? F naught going to be how much? That is going to be 72 hertz. F naught 72 means how much you are F. F naught 72 hertz means what is your F value? 76. 76. Done and dusted. I think tutor is fully finished, right? Tutor is fully discussed, fully finished. Entire tutor is completely discussed. Another tutor is there. Right, along with that tutor, I am supposed giving that essay questions also in the next tutor. Next tutor, we are giving that questions also. That means essay questions also will be included in the next tutor. It will be posted mostly next Monday if it is possible. If not, before next week, we will post the tutor. Okay, genuinely put some replies. I think we have done every question. Right, we have done lots of questions. This type of work is, I think, no one is doing in this level. Right, no one is doing. They are doing just few past paper questions, 1 or 2. But I am not like that. Normally, when I do something, I try my maximum to do everything properly. Try my maximum. Right, I never put an effort this much to any of my previous batches. Is my so far the as a batch the biggest effort I put on this 2026 batch only. 2027 I will put more and more. Okay, right, I want to do this batch very properly. Right till the last moment. Put some replies, all good. 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 If all okay, put some reply. All okay, right? All okay. All nice. Okay, now what shall we do now? What shall we do now? Okay, now I'll wind up. We'll stop for now. Right, but I told you, I will do long hour classes from February. Today we'll stop for now. Next week onwards for sure. We'll start from optics and Doppler questions then. And next day onwards we will do more long duration. So temporarily I will stop now. Study will please once again read these questions and get the practice. The most important thing is after doing these questions, what you felt important. Some tricks is proportionality methods. These ideas put in your mind. If you have a doubt, we'll arrange a kind of session and we'll discuss the stories. Right? Sometimes better if we can arrange a Zoom session. Sometimes when you ask a doubt, sometimes I don't quickly reply. In that case, we can have come to a Zoom session and we can clarify our doubts. We can have a session like that. If you all coming and telling, we can have a session like that. Okay, we'll plan something like that and we'll do the story beautifully. But I will stop for now. The study will quickly I'm stopping. Okay, then good night, my dear students.